Friends, welcome to the paper of numerical methods in the subject of information technology under EPG Pathshala. Today, we are going to learn successive approximation method to find roots of an equation. Already we have learned different methods, namely bisection method, method of false position, Newton-Raphson method, second method. And today, we are going to add one more feather in the cap, namely successive approximation method or fixed point method. This fixed point method is a very simple method. I would rather call it simpler than even bisection method. Bisection method and false position method, you already know that they guarantee convergence, and second method and Newton-Raphson method do not guarantee convergence. This method is very simple. It is open method. It does not guarantee convergence as such, but if initial approximation is chosen properly and the function g is chosen properly, then convergence can be ensured. So, today let us learn about this method. It is very interesting method. This method is based on fixed point theorem, and that is why it is called fixed point method. So, let us understand what is a fixed point first. So, this is based on the fixed point concept. So, what is a fixed point? Say fixed point of a function is a real number such that function does not change its value at that point. In other words, the argument and the value of function remains same, that is x equal to, it is a root of x equal to f x. Let us take some examples to understand the fixed point. Take a very simple example of the function. Let us say it is x square. Let us find the fixed point of the function f x equal to x square. So, to find the fixed point of the function f x equal to x square, we will get x square equal to x, and we take all the terms on one side, x square minus x is 0. So, x into x minus 1 is 0. So, x is 0 or x is 1. So, the function f x equal to x square has two fixed points, namely 0 and 1. You can verify also, see when f x is 0, 0 is equal to x square is also 0, x is also 0. So, if 0 satisfies x equal to x square. Similarly, when x is 1, x equal to 1, x square is also equal to 1, it satisfies x equal to x square. Let us take another illustration where f x is equal to c x into 1 minus x, and we want to find fixed point of this function c x into 1 minus x. So, we will equate c x into 1 minus x equal to x to find the fixed point, and x cancels, either x is 0 or if x is not 0, we get c into 1 minus x should be equal to 1, and c into 1 minus x equal to 1 gives 1 minus x is 1 by c. Taking c on the other side, we are assuming c is non-zero, and so x is given by 1 minus 1 upon c, and that is c minus 1 by c. And therefore, the fixed points of g x are given by in terms of constant c as c x are 0 and c minus 1 by c. Now, see in these two examples which we have chosen, we got two fixed points. Question is whether a function will always have a fixed point or not, or whether there can be a unique fixed point or there can be more than one fixed point. We will answer this question. Before that, let us understand graphically what a fixed point of a function means. So, see if we graphically, see we want to find root of x equal to g x. So, we plot the line y equal to x, which is a straight line making an angle of 45 degree with the x axis, and you can see the curve y equal to g x is drawn on the screen. See the point at which the y equal to g x intersects with the line y equal to x, the x abscissa of those 2 points are the fixed points of the function, because see the point where the intersect, let us say the coordinates are, because straight line is y equal to x. So, x y 1 equal to x y 2, because y 1 is x curve and y 2 is g x. Now, y 1 is x, so x x is x g x, equating these two pairs we get x equal to g x. So, at the point of intersection of y equal to x and y equal to g x gives us the fixed point of the function y equal to g x. So, what our conclusion is that x square and Cx into 1 minus x had two fixed points. See, a function need not, see the first question is whether each and every function has a fixed point. So, answer is each and every function need not have a fixed point, and as an example of this we have the function x square plus 1. So, if I equate x square plus 1 equal to x and you try to solve it, x square minus x plus 1 equal to 0, this does not have a real root. You can apply the quadratic equation finding root method, ax square plus bx plus c equal to 0, and you will get the roots as complex roots. There is no real root of x square minus x plus 1 equal to 0. Even otherwise also you can visualize x square plus 1 can never be equal to x, and as a result x square plus 1 does not have any fixed point. Similarly, another function e raised to x ln x also does not have any fixed point. So, a function may not have a fixed point, may have a unique fixed point, we will come to that example little later, or may have more than one fixed point. Our method, this method of successive approximation method, rests upon finding fixed point of a equation when we express f x equal to 0 in the form of x equal to 0 g x. So, the method consists of expressing f x equal to 0 in the form of x equal to g x, and the root of f x equal to 0 will satisfy the equation x equal to g x. So, the root of f x equal to 0 is nothing but the fixed point of the function g x. So, our root finding problem gets converted to problem of finding fixed point of the function g x. So, our iterative scheme of this successive approximation method is make an initial guess x 0. The method of making the initial guess x 0 can be same as we have employed in our other previous methods. The similar technique can be used to making an initial guess x 0 so that the x 0 is quite near the root, and then we find successive approximations. The sequence of approximations are given by the equation x n plus 1 is equal to g x n. That is, x 1 will be g x 0, x 2 will be g x 1, x 3 will be g x 2, and so on. And when these x n's converge to a point when the two consecutive x are less than epsilon, will stop the process, and that will give us the estimate of the root of the equation f x equal to 0, and that is a fixed point of g x. So, this function g x we should be calling iteration function. So, the next question which arises is that the method consists of expressing f x equal to 0 as x equal to g x, that is the first step. Is it always feasible? Can we always express f x equal to 0 as x equal to g x? Answer is yes. One very obvious method is add x on both the sides, because the equation is g x x equal to f x equal to 0. So, you add x on both the sides, which gives us x is equal to f x plus x. So, g x will take the role of f x plus x. So, there are of course many ways of transforming this g x equal to f x equal to 0 in the form x equal to g x. One way always exists. Let us take one practical example to see that there are more than one method practically to express x as g x. Let us take the same example which we have taken in our previous modules, the equation x cube plus x minus 1 equal to 0. In this equation we can express this equation f x equal to 0 as x equal to g x in many different ways. One is simply take 1 minus x cube on the other side and retain x on the left side, giving us x equal to 1 minus x cube. The second is, as suggested, add x on both the sides, f x equal to 0. So, x is equal to f x plus x. So, g x will become f x plus x. So, if we add x on both the sides, we get x is equal to x cube plus 2 x minus 1. Still, third way is, in this example, I keep x cube on the left side and take the other terms on the right side, giving me x cube as 1 minus x, and so x is the cube root of 1 minus x, giving x as 1 minus x raised to 1 by 3. And still there is one more way. I take 1 on the right side, left side is x cube plus x, and take x common. So, we get x into 1 plus x square is equal to x, giving us x as 1 upon 1 plus x square. So, in this simple example, we have been able to express very easily x equal to g x in 4 ways. The question is, how do these different g's perform when we apply the formula x n plus 1 is equal to g x n? Do all give the root? Do all converge? All sequences of approximations converge to the root, or none of them converges, or do some of them converge? And if some of them converge, what can be the criteria of selection proper value of g x? So, let us go, let us see one by one. See, if we look at the leftmost table, that is g x is 1 minus s cube in this. So, x is 1 minus x cube we have expressed, and already as we know, we may begin with the initial guess x equal to 0 as we have done in the previous modules. And if you find, see, when x is 0, g x is 1 minus x cube. So, 1 minus 0, it gives 1. Now, this x 1 g x is x 1. So, 1 becomes the input to the function. So, when we put x equal to 1, I get 1 minus 1 as 0. So, next point is 0. So, 0, again 0 is the input, 1 minus 0 is 1. So, the values keep on sequence of approximations are oscillating between 0, 1, 0, 1, 0, 1 and so on. And so, this method, this g x will not give the root of the equation. Let us take the second one, g x as x cube plus 2 x minus 1. In this case, when I put x equal to 1, g x becomes 1 plus 2 minus 1, that is 2. This 2 will become the input for the next iteration, because the value of g is our g of x 1 becomes x 2. So, it is 2. So, if I put x equal to 2, I get 2 cube plus 2 into 2, 8 plus 2 into 2, 4, 12, 12 minus 1, 11. So, our x 2 becomes 11, 11 will be the input for the next iteration. So, g of x 2 will be x 3 and that becomes 1352, and next it is further very high figure 2, 4, 7, 1, 3, 2, 9, 0, 2, 4. And so, you can very well guess that here also the sequence of approximations are not converging. In fact, the sequence of approximations go on increasing and they are tending towards infinity. So, this sequence of approximations also does not give us the root. Let us look at the third form of g x, and the third form of g x is 1 minus x raised to 1 by 3. Here, if we begin initial value of x equal to 0, the 1 minus x becomes 1, cube root is 1. So, next input is 1. If I put 1, 1 minus 1, 0. So, again here the oscillating values are oscillating between 0 and 1. Of course, if I change the initial guess from 0 to some other value, the values need not oscillate between 0 and 1, but still the method is not giving a proper way of convergence. Let us look, only one form of g x now remains, and that form of g x is 1 upon 1 plus x square. If I take g x as 1 upon 1 plus x square, you can look at the table, x is 0, g x is 1. Now, 1 becomes the input, 1 upon 1 plus 1. So, 1 upon 2 becomes 0.5, 0.5 becomes the input for the next iteration. So, 1 upon 1 plus 0.5 square, that is 0.25. So, 1.25 it becomes 0.8, and then 0.8 becomes the input, 1 upon 1 plus 0.8 square. So, that becomes 0.06097756. So, here the sequence of approximation slowly and slowly, if you look at the table, it is converging, they are become steady and become steady to 0.68, then 0.682, ultimately 7.682328. So, here it has converged. Of course, the convergence has become is quite slow, but the method has converged with this choice of g x 1 upon 1 plus x square, and the sequence of approximations converges to the root of the equation x cube plus x minus 1, namely giving the root as 0.682328. And this stresses that one needs to choose an appropriate function g x, so that the sequence of approximations not only converges, but converges fast if possible. So, first is we would like to ensure that the sequence of approximation converges, and if possible, if more than one g can give us convergence, then what should be the function g x, which one we should we choose, so that the fastest convergence among all possible proper choices of g x can be achieved. So, let us look at some results to guide us. The results which to guide us were known as the existence and uniqueness theorem of the fixed point. This theorem states that if G is continuous on a closed interval a b, its range is also the interval a b, then G has a fixed point. So, it guarantees us the fixed point if the function G is continuous on the interval a b with its values also the function lying in the interval a b. And the second tells us about the second point in this theorem tells us about that the nature of the fixed point, the number of fixed point will be unique in the case G is differentiable on the open interval a b and the value of derivative of G on the entire interval can be said to be less than equal to a constant k which is less than 1. In other words, the derivative of G absolute value means the numerically the value of derivative of G is less than 1, in that case the function G will have a unique fixed point. The first part of the theorem's proof is based on the intermediate value theorem, which we have already learned in the introductory module, and the second part the proof is based on the mean value theorem. Now, the second part is the second theorem which helps us to tell us that about this derivative of G, and this theorem tells us that if your G is continuous on the closed interval a b with the domain and range both lying in the interval a b and G is differentiable on the open interval a b with value of G numerically lying less than 1 on the entire open interval a b, then this sequence of approximations which we have used in our formula x n plus 1 is equal to G x n, then this will converge to fixed point. So, this ensures that if the value of derivative is numerically less than 1, then the sequence of approximations will converge to the root. This also tells us about idea about the rate of convergence, that if the two consecutive approximations absolute value of x n minus 1 will be given by less than equal to k raised to n multiplied by the constant which is nothing but the maximum of x 0 minus a and b minus x 0. X 0 we know is the initial guess, a and b is the interval over which we are considering. So, this also gives us the idea the smaller the k, better will be the convergence, because if k is small, k raised to n will be small and so faster will be the convergence. So, this theorem tells us that if value of derivative is less than 1, the sequence of approximation will give us convergence, and the smaller the k, better would be the pace, better would be the speed of convergence. So, if we want to ensure convergence, then we should choose G the function. If we have more than one options available about the choice of g x, we should choose the function g x in such that the derivative of g is less than equal to 1 numerically on the interval under consideration within which the root lies. Of course, we are going to always get the equation f x equal to 0 in the form of an equation. Definitely f x is going to be continuous and it is going to be differentiable on the interval a b. The way we choose in the earlier methods, we will find the a and b, so that the root lies within a b. So, function is going to be continuous, function is going to be differentiable. Now, only we have to look for the different ways of writing f x equal to 0 in the form of x equal to g x. Once we do this, then we have to select g x in such a way that the value of derivative numerical is less than 1, and if more than one such g's are available, then the smaller the value of derivative, better would be the pace. So, these two theorems help guide us in selecting proper g x. And last, see, the point gives us that x n minus c, c is the root, is less than equal to k raised to n by 1 minus k into mod x 1 minus x 0. So, this also figure tells us the k value smaller is better, and you can very well note if k is half, then it is very similar, because if the interval, the error term is always similar to, very much resembles the bisection method. The stopping criteria can be used the same as we have employed in the earlier methods. Any of the stopping criteria can be used. Most probably, if you require the answer correct to certain number of decimal places, one can use the epsilon tolerance, that is, one may stop when the difference between two consecutive approximations is absolute wise less than the epsilon tolerance that you decide. So, this is the, in a nut and shell, the algorithm our input will be the fx given function and will express on our own fx as x equal to gx. Proper gx has to be chosen, initial guess has to be determined. So, x0 will be the initial guess, gx will be the function. How much accurate we want the answer. So, epsilon tolerance will be the input, and see, though the gx will be chosen so that the method converges, nevertheless the theorem which we have stated is a theorem which gives us sufficient convergence. It tells us that if the value of derivative is less than 1, the method will converge, but this is not necessary. It does not tell us that if the derivative is not less than 1, the method will diverge, then it may converge or may diverge. In case we are not able to get such g such that the numerically derivative of g is less than 1, we can definitely take a chance to work with the other g and see what results are. And therefore, it is very important to keep an upper cap on the number of iterations to be performed, so that if the method does not converge in those number of iterations, one should get the message that the method does not converge. So, we have the input, we have to input capital N as the maximum number of iterations. We begin k equal to 0 and our iterative x1 will be equal to gx0. So, iteration is xk plus 1 equal to gxk, and if xk plus 1 minus xk absolute wise is less than epsilon, that means we have reached the root to correct decimal places, will output as the estimate of the root as xk plus 1, will exit it, otherwise will increment k equal to k plus 1. We check whether we have not reached the upper limit on the number of iterations. If yes, we have to come out and display that it does not converge, otherwise we will again go on and will come out till we have got the root correct to desired decimal places. Now, with this knowledge, let us take another example, and as fx equal to x raised to 4 minus x minus 10. Let us try to find the root of this equation x4 raised to minus x minus 10 equal to 0. We need to find the interval a b over which we need to ensure that the convergence occurs. So, let us find the values of function at different points. At 0, if you observe, 0 minus 0 is minus 10, function is minus 10. At 1 f1, if I substitute 1 minus 1 minus 10, again f1 is negative minus 10, f0 and f1 at both the points function is negative given by minus 10. If I put x equal to 2, it is 2 raised to 4 16 minus 2 14 minus 10 4. So, f2 is 4. So, function has changed its signs between 1 and 2. So, it ensures that the root lies between 1 and 2, because function has changed its sign from negative to positive. So, our interval of consideration would be the interval 1 2. Now, let us transform fx equal to 0 in the form of x equal to gx, and let us see what are the different ways. See, again x raised to 4 minus x minus 10 equal to 0, the simplest looks retain x on one side, other terms on the other side. So, we get x is equal to x raised to 4 minus 10. The second is keep x raised to 4 on the left and take other terms on the right side, which gives x raised to 4 is x plus 10. So, x is x plus 10 raised to 1 by 4, fourth root of x plus 10. And the third is take 10 on the right side. So, we get x raised to 4 minus x as 10, and in the left side take x common. So, x into x cube minus 1 is equal to 10, giving us x as 10 upon x cube minus 1. So, we have obtained 3 ways of expressing fx equal to 0, x raised to 4 minus x minus 10 equal to 0 in the form x equal to gx. Now, let us take one by one. The first one is x equal to x raised to 4 minus 10. If we take derivative of this, we get g dash is 4x cube. Our interval is 1 to 2. 4x cube is an increasing function. As x increases, the values increase. If I put x equal to 1, the function is 4, and as x will increase, the values will increase, and so this derivative is never going to be less than 1, no question. So, it's doubtful whether this value of g will give us convergence. Let us look at the second one, and that is x is equal to x plus 10 raised to 1 by 4. So, if I look at x equal to x plus 10 raised to 1 by 4, we take the derivative 1 by 4 into x plus 10 raised to minus 3 by 4, and that also when we substitute the values, this also expression does not remain less than 1 numerically. The third one, gx equal to 10 by x cube minus 1, if we take the derivative, 10 is constant, x cube minus 1 raised to minus 1 gives us minus 1 into x cube minus 1 raised to minus 2 into derivative of x cube minus 1 is 3x square, and this value of g dash x should give us less than equal to 1. So, let us take the example of f x equal to x raised to 4 minus x minus 10. Let us try to express this in the form of x equal to g x. See, the simplest way is keep x on one side, other terms on the other side, gives us x equal to x raised to 4 minus 10. The other way is keep x raised to 4 on one side and take x plus 10 on the other side, giving us x equal to x plus 10 raised to 1 by 4. And the third is take 10 on the other side, giving us x raised to 4 minus x equal to 10. We take x common, so x into x cube minus 1 is equal to 10, giving us x equal to 10 upon x cube minus 1. So, these are the three options. Let us first look at the option number 1 and option number 3. In case of option number 1, gx is x raised to 4 minus 10, as we have written x as x raised to 4 minus 10. So, g dash x is derivative of x raised to 4, 4x cube minus 0, so 4x cube, and this 4x cube, the value on the interval 1 to 2 is never going to be less than 1. At 1, the value is 4, and 4x cube is an increasing function. As x increases, the value will go on increasing, and so the value will be always greater than 4, no question of becoming the value to be less than 1. As a result, this choice of gx will not guarantee us convergence. Let us look at the third, x equal to 10 upon x cube minus 1. Here gx is 10 into x cube minus 1 raised to minus 1. We differentiate it. So, 10 as it is, minus 1 into x cube minus 1 raised to minus 2 multiplied by derivative of x cube, that is 3x square. This also term, that is 10 3x square upon x cube minus 1 raised to square on the interval 1 to 2 does not remain less than 1 on this interval, and so this also does not guarantee us convergence. So, let us first these two cases, let us try to solve them. See, the root lies between 1 and 2, we take our initial guess as the midpoint of the interval 1 2, so 0.5. And the first table, if you look at it, is gx is 10 upon x square x cube minus 1. And if we look at the values 1.5, the gx become 10 upon 1.5 square minus 1 gives 4.210526. This will become the input for the second iteration, then the gx comes out to be 0.135784. That becomes the input for the third, the value of g becomes minus 10.025098, and the values are just, you can see that these are leading us to nowhere, they are just oscillating between 0 and minus 1. So, here the oscillation is taking place 0 minus 1, 0 minus 1, 0 minus 1, and the method is not converging. The derivative is not less than 1. So, convergence was not guaranteed, and that is what is happening. Let us look at the second gx, that is x raised to 4 minus 10. If I input again 1.5 here, x raised to 4 minus 10 is minus 4.93, and minus 4.93 becomes the input for the next iteration, and the values is 584. 584 becomes the input 1352, and again here the values are increasing without bound, the sequence of approximation is tending to plus infinity, and the method is diverging. So, these two gx derivative was not less than 1, and so that tallies with the theorem's result that it is not guaranteeing us convergence. In fact, convergence is not taking place. Let us look at the third choice of gx, and that is x plus 10 raised to 1 by 4. If I differentiate gx, I get 1 by 4 x plus 10 raised to minus 3 by 4. Here, if we look at the interval 1 to 2, see on the interval 1 to 2, x plus 10 will be greater than 11 for x greater than 1. So, x plus 10 raised to 3 by 4 will be greater than 11 raised to 3 by 4, and 1 upon x plus 10 raised to 3 by 4 divided by 4 will be less than 1 by 4, 11 raised to 3 by 4. So, 1 by 4, 1331 raised to 1 by 4, and this number can be verified to be less than 1 by 4, less than 1, and so that by our theorem's result should ensure us convergence. Let us solve it, let us verify it. See, if I put x equal to 1.5, you can see that there are 4 tables and their 4 tables are shown with the different initial guesses of x. So, first at 1.5, you can see the gx at 1.5 is 1.841512, which becomes the input. It becomes 1.855034, which becomes the input for the third iteration. The value obtained is 1.855563 and so on, and in fact, in 6 iterations the method has converged to 6 decimal places, giving the root 1.855585. Not only this, we have taken in the second case the initial guess as x equal to 2 in the second table, and the root lies between 1 and 2, you see it, and again in 5 iterations the method has converged. Taking initial guess at once, so 2 endpoints we have chosen 1 and 2, again the method is converging in 6 iterations, and finally see the initial guess is 4. So, root does not lie, means the initial guess is quite far from the interval. Even then in 7 iterations the method is converging to 6 decimal places. So, convergence has been very rapid in this example and very simple table, just evaluation of gx, and we have been able to evaluate only by evaluating gx we get the next sequence of approximation, and the method is converging very fast, and it is also open method, there is no restriction for the initial choice. So, but only thing is that in this method gx has to be properly selected. If gx is not proper, the method may diverge, but if we have been able to land in such a function of gx where derivative of absolute value of derivative is less than 1, then the method converges very fast. As a second illustration, let us take f x equal to 3x minus cos x minus 1. Here f 0 is 3 into 0 0 minus cos 0 1 minus 2 negative, f pi by 2 if I take it, because pi by 2 we are taking because cos, to evaluate cos is easy manually. So, 3 pi by 2 minus 1, it is positive. So, the root lies between 0 and pi by 2, and rewriting this equation in the form x equal to gx, I retain x on the left side, 3x is 1 plus cos x, gives me x is 1 plus cos x by 3. Let us again verify the value of derivative of g. See, whenever function is given by an equation, function is continuous and differentiable, so that we do not have to worry. All we need to worry is about the value of derivative. So, g dash x is minus 1 by 3 sin x. We know the value of sin x always lies between minus 1 and plus 1. So, absolute value of g dash is less than equal to 1 by 3 into 1, it is always bounded by 1 by 3. So, the method guarantees us convergence. We make an initial guess as it just as simple x 0 equal to 0 without even bothering where the root lies. So, you can see that in this table the first iteration gives the value of g at 0 as 0.666667. That becomes the input for the next iteration. So, value is 0.595296, and subsequently the method has converged to 0.607102 quite fast. Let us come to the graphical representation of this method. We have learned the method, the algorithm, we have also solved example. What does this method stand graphically? What is being done in this method through graphically? So, we have, see, we know that we are finding fixed point when we express f x as x equal to g x. So, how do we get the fixed point? The fixed point is nothing but the intersection of the line y equal to x and y equal to g x. So, in this graph, see, you have the line y equal to x and we have the graph y equal to g x. Let us say we begin with initial guess x 0. This initial guess x 0, we move to the curve. When we move to the curve, we get the point x is x 0, on the curve y is g x. So, the point is x 0 g x 0. I want x 1 as g x 0. To get x 1 as g x 0, basically of this point's y coordinate I want. So, I move horizontally to the straight line y equal to x. When we move horizontally to the straight line y equal to x, see, what will change is our x coordinate will change, y coordinate remains the same. So, on the line y coordinate is g x 0 and x coordinate y is x. So, x coordinate is also g x 0. So, the point of intersection here, the point where this horizontal line meets is the point g x 0 g x 0. So, this point we can call it the abscissa point as x 1. So, the point x 1, the dotted line, that is the value of x 1 on the x axis. So, x 1, how to get x 1 from x 0? We have moved vertically to the curve and then horizontally to the straight line y equal to x. Similarly, to get x 2 from x 1, we will move vertically to the curve. So, when we move vertically to the curve y equal to g x, we get the point x is x 1. So, the point where this vertical line meets the curve is x 1 g x 1, and we will move horizontally to the straight line. So, when we move horizontally to the straight line, the point which we will get will be g x 1 g x 1, because x coordinate will change, y coordinate will remain the same. So, this is our point x equal to x 2. So, basically to get the next iteration, the steps are we move vertically to the curve and horizontally to the straight line, vertically to the curve, horizontally to the straight line. So, next iteration vertically to the curve and then horizontally to the straight line, and you can very well see that we are moving, the point of intersection is we have reached very near. So, this is how we are reaching the root, and this convergence, this form of convergence is known as a stepwise convergence. See this diagram which we have made, if you can very well see, the y equal to g curve, the slope which has been made in this slope is, the derivative is definitely less than 1 and it is also positive. So, the case where derivative is positive and less than 1, the convergence is taking place and the movement is stepwise. The movement takes place vertical to the curve, horizontal to the straight line, vertical to the curve, horizontal to the straight line, and that is why it is known as stepwise convergence. So, this type of convergence is called stepwise convergence, which occurs in the case where the derivative of g dash x is positive and less than 1. And if we look at the sequence x 0, x 1, x 2, x 3, you can see that they are steadily reaching to the root. So, they go on tending towards the root in one direction. The sequence of approximations approach the root, may be increasing or may be decreasing as the case may be. Let us take the second case here, that is, so in the case of 0 less than g dash x less than 1, we have observed it is stepwise convergence and they steadily, the sequence of approximations move towards the root. Now, the second case let us take, where the slope is greater than 1, it is positive, definitely greater than 1. So, it is a vertical more steep curve it is. So, here again if we begin the guess, then let us say, see the point of intersection of the line is the root. We have made initial guess quite near the root, if you observe in the slide on the screen, and we again move vertical to the curve, we move horizontal to the straight line, vertical to the curve, horizontal to the straight line. So, as we move, you can very well observe what is happening is, we instead of moving towards the root, we have moved away from the root. So, this because the derivative is greater than 1, convergence is not taking place, rather than the values are moving steadily away from the root in one direction. And when we solve previous examples, you could have found that many times the values in certain g x, the values were tending towards infinity, plus infinity or minus infinity steadily. So, that was the case where derivative was numerically greater than 1. So, this is known as, again the method of movement is stepwise. So, it is called stepwise divergence. So, stepwise occurs when the derivative of g is positive. If less than 1, stepwise convergence occurs. If greater than 1, stepwise divergence occurs. Let us take the third case when the derivative is negative, but numerically less than 1. So, here if you look at the curve y equal to g x, here the derivative of g is tangent of the slope, that is negative, and again we begin with the initial guess not quite near the root. So, we make the initial guess x 0, movement is same as we discussed in the previous graphs, we had to move vertical to the curve giving x 0 g x 0, horizontal to the straight line giving us g x 0 g x 0, the x coordinate corresponding to if is our the approximation x 1. Again we move vertical to the curve, horizontal to the straight line, and the x point gives us the next approximation. Again vertical to the curve, horizontal to the straight line, and that x point gives us the next approximation. So, here you will find that when we proceed this way, we are again approaching the point of intersection of the line y equal to x and y equal to g x, but this time see what is happening is the values, the sequence of approximations are oscillating about the root, that is x 0, then x 1, x 2, x 3, x 4, x 5, x 6, x 7, x so on. So, they are approaching the root, but by movement oscillating from one side to the other side of the root like pendulum, and this swing of the pendulum as if it goes on becoming smaller and smaller and approaches the root. So, in this case, and if you look at the graph of vertical to the curve, horizontal to the straight line, see this is like a spiral. Of course, spiral is round, but this is square spiral, that is rectangular spiral, and moving falling down to the core inside near the root, and that is why this convergence is known as spiral convergence. And last case, let us take when the derivative g dash x is less than minus 1. So, numerically it is greater than 1, but the g dash x is negative. And so, you can look at the curve we have plotted y equal to g x, where derivative is less than minus 1, numerically derivative is greater than 1. And here see, you look it again, we have begin with the x 0 as quite near the root, near the point of intersection, and again we will repeat the same steps, vertical to the curve, horizontal to the straight line, vertical to the curve, horizontal to the straight line, and we get the subsequent points, right. But this time if you look, you find it we are moving farther and farther away from the root, and that gave us the again the movement was spiral here, but we were moving on the other two sides, but the away from the roots. So, the movement is this way, we are moving away on one side, then the other side the pendulum swing goes on increasing, and so this is a divergence case, and this is known as spiral divergence. So, we have stepwise convergence, stepwise divergence in case of positive g dash, and we have spiral convergence and spiral divergence in case of negative value of g dash x. So, let us look at the advantages of this successive approximation method. It is very simple, I think simpler than bisection method once we have landed in a proper choice of g x, and it also has the advantage that there is no such restriction of choosing g x 0 so that it lies within a particular interval. So, it is an open method, very easy to apply, very simple, and if we are lucky to get g such that the value of g dash x is small, it gives us very rapid convergence. The only thing is we should be able to get a proper g x. So, what are the disadvantages? That is, it will require a skill, or some equations may not be able to give you such g x, or it requires some computations to, because you have to transform the equation f is equal to 0 in the form x equal to g x and check that the derivative lies less than 1, try to ensure it. So, that requires a pre-computation work before applying a successive approximation method, and of course, the rate of convergence, the pace of convergence will depend upon the choice of g x. So, if we cannot get a good g x in terms of rate of convergence, the number of iterations can also become large. So, this is about the successive approximation method we have learned, and in our next module we are going to talk about a special case of f x, and that is the roots of polynomial, because polynomials play a very important role, and for polynomials all the methods which we have learned are applicable, but then there are special methods for polynomials to find all the roots of a polynomial. So, we would like to focus on this special case of the root of polynomials in our next module. Bye till then, happy reading, bye bye.